Morning. Sorry, I was running a little bit late. I need to put my. Can I use my laptop? Oh, okay. I need to use. So, first, let me introduce myself. I'm Bernard Wynn. I'm a director of engineering at NVIDIA, and I'm responsible for, I oversee the development of NeMo Framework. Today, I want to speak with you about advancing LLM training at scale. I'll be talking about the process of taking a model from pre-training through fine-tuning through post-training and some of the libraries and open source AI that NVIDIA offers to help facilitate this. All right. So I'll just begin. Maybe you've seen this slide. It's a good level setting context for this presentation. Uh, so in the beginning of LLM model training, a lot of the focus was on scaling pre-training models. And that was essentially, we saw scaling laws where the larger you make the model, the more intelligent it would become. Now, if you follow this to the logical conclusion, if I want my model to be extremely intelligent, then it needs to keep getting bigger and bigger and bigger. But that's not particularly practical because at some point you run out of resources and you want to deploy these models on edge devices, and you cannot fit these super large models on such environments. So there was an advent of post-training scaling. This is where you can take a pre-trained large model and adapt it to a specific domain. You can even shrink down that model and make it fit, but the model is still trained to be more of um, without reasoning and thinking. So many of you are probably familiar with ChatGPT or other such AI applications where now the models can actually think. So it takes time. You can ask it to think harder about a question or a prompt, and it'll give a more intelligent answer. So how do you enable a model to become thinking? And that's what's happening in this post-training to test time scaling long thinking. So we'll spend some time talking about this particular latter half. Before we do that, I'd like to take some time to talk about just open source AI and NVIDIA's stance towards it. So open source software has been around for a long time. I mean, since days of Linux, but AI has not been open source that long. For example, a lot of the models and applications that we use, ChatGPT is not open source. So recently, AI has become more and more open source. Um, what you're seeing is an explosion of more models being developed and then released out in the open. Now, there are different definitions of open source when it comes to models. For example, there are models where you get access to the weights. So you download the weights, you can take the model, uh, deploy the model architecture and the weights, and you can run it. But if I want to, say, fine tune that model, or if I want to retrain that model, if I want to know what was the recipe to train that model, that's not always made available with the model weights. So when I am talking about open source with respect to NVIDIA's stance towards open source AI, NVIDIA is wanting to provide all of the things required to train the model. So not just the model and the weights, also the data sets, the recipes, the libraries that were used to train those models. I might be missing anything, but yeah, we try to provide everything that you need to learn and reproduce the models that come out of NVIDIA. Sorry, I'm just gonna turn off my phone. Um, so there's a number of areas that we open source software, from health AI to physics to agentic AI. We'll spend most of our time talking today about Nemotron. Also, Cosmos for physical AI, Groot robotics, and AV. Jensen spent quite a bit of time talking about Alpamayo at the CES in January. And you can see here, as far as GitHub repositories, NVIDIA is leading by far as the total number of repositories. So just to reinforce, data, models, libraries, training scripts, which are the recipes in which to take these libraries and train the models, and blueprints in which you can take the models and piece together them into solutions. So Nemotron, uh, this is a fine balance that we're trying to make with Nemotron, where we try to make it efficient, intelligent, and open. And I'll show some leaderboard charts later to demonstrate that. So for example, Nemotron 3 Nano was a model that we released most recently. There is Super and Ultra coming out soon. Nano 3 in its weight class, so this is a 30B this is a 30 billion parameter model. Um, the closest models that are in this class would be GPTOS 20B and Qwen 3 30B. You can see that NVIDIA's Nemotron 3 is at least or more intelligent than these. Now, where NVIDIA really spends time is on efficiency. So when we're talking about efficiency, we're talking about tokens and the number of tokens that you can get out of the model with the least amount of compute. Or put another way, which models given a certain compute can give you the most tokens output. Here you can see that Nemotron 3 Nano provides 350, 60 tokens per second, which is much higher than other models. And so what this means is you can essentially ask more prompts to this model in a certain period of time for less cost. As I mentioned, Nano 3 is already available. Super and Ultra are coming soon. Super very soon, and then Ultra as a short follow. And so these are MOE architectures. So even though the total number of parameters is much larger, like 30B, 100, 500, how we achieve the efficiency is that at inference time, only a small portion of the total parameters are actually active. So A3B means only 3 billion parameters are active out of the 30B. And this is leveraging the mixture of experts architecture. Same with 100B, only 10B are active, 550B. So 10% essentially of the parameters are active during inference time. I'm going to transition into agentic AI and how agentic AI is, how post-training and reasoning is required for agentic AI. So agentic AI is essentially models where an AI agent can act on behalf to accomplish a set of tasks or goals. This example is where a user is interacting with an agent via speech. So I'm talking to this agent. This agent is then guiding um, certain tasks and decisions to different LMs in the back. So language models, vision language models, reasoning models, accessing data, uh, accomplishing a job, and then routing it back from speech back to text. Now, or sorry, text to speech. Um, Nemotron, we have different models for reasoning, vision, information retrieval, content safety, and speech. So what we're trying to, what I'm trying to share here is that is there a broad portfolio of Nemotron models that you can use for your agentic AI. So you can take a lot of these models and piece them into an agentic AI architecture. The data, just a little bit more detail on that. We provide, yeah, essentially all of these are different data sets that are available on open source via GitHub. I want to get through some other slides. These are some examples of blueprints. This one is essentially user interacting with an agent to do report generation. Give me a report on. I think this is probably functionality that folks might be used to already. If you use deep thinking on any of the most recent AI chats applications, you can ask it to do deep research for you, and it'll come back with a full report in a couple minutes of a subject that might have taken hours to Google and compile on your own. And this is a blueprint for how to implement this yourself. Same, there's searching through hours of video and then summarizing. Um, this is another agentic AI use case and a blueprint for it. So let's dive deeper into AI agents specifically. So we have starting with a prompt. So what do I want my agent to do? For example, plan me an itinerary and keep it within a certain budget over a number of days. And so the agent will do a cycle of perception, understanding my prompt, reasoning through it, and then taking a course of action. The agent may use tools such as search to go search the web, calculators to calculate things. You can even run code through Python interpreters, essentially any tool that can be made available through a protocol. There's protocols such as MCP, where you can enable any kind of web service to be accessible from an agent. Agents can also even directly use your computer. If you give it access, it can access the local file system. It can search files and your information for you and use that as part of the planning context. Memory is an important aspect of agentic AI because you might have many agents acting in concert together. The agents, a more brute force way is the agent passes all the data from one to another over the network. That will be very expensive and slow. But if you can run, say, deploy all of your agents in something like a rack scale, Grace Blackwell rack, for example, all the GPUs can share the memory together. And so the agents, you could have a whole agent ecosystem running in a GPU rack and sharing the context over high-speed NVLink. Agents can also talk to other agents. And you can have specialized agents. You can have like a travel booking service agent speaking with an agent that is really good at planning rental cars. I mean, I'm giving kind of simple examples, but you can imagine there will be specialized agents. Speaking of specialized agents, so let's see. We were talking about larger models, and now we're talking about smaller models. And this is where you can create more specialized small models And these models, small models, can be used to power these specialized agents. It's much, these small models can be much more domain specific. They can be adapted, and they're very cost efficient. And yeah, the data IP control, this is assuming that, yeah, you're running your agent in a data center, either that you trust that you're operating, or with a cloud service provider that is also trusted. That would be part of the sovereign AI theme also that we've been discussing at this conference. Okay, kind of, these are just examples of different specialized agents. All right, let's get more into post-training. So post-training is essentially taking an existing model that you've either pre-trained from scratch yourself, or say downloaded from open source, and giving it additional capabilities, aligning it. You can make the model more helpful and, say, less harmful. A little bit of the recent evolution of post-training. So in the beginning, there was essentially just taking a model and being able to predict the next token. This is just text completion. Then with ChatGPT, I think we all saw that become a first in where you can have a conversation with a model. And this was essentially taking that model and teaching it how to have a multi-turn conversation. Then the next wave was, okay, now I can do the multi-turn conversation, but please think before you respond. And so thinking and reasoning was added into these language models. Now, where we are today with agentic AI is the reasoning can lead to multiple steps. So there can be a multiple course of action, and the agents can use tools, which we discussed previously. Where we are headed, if you ask me, in the next year or so, we want to get to a longer horizon. So what does that mean? Let me go to the next slide and we can talk about that more. So today, this is actually a little bit out of date. GPT, we're at GPT 5.2 now, as of early February. And I believe Claude Sonnet 4.6 was just released yesterday. Yeah. Okay, 4.6, yes. So the AI field is moving fast. That said, the point of this slide is basically trying to explain that these are models where, so context, or horizon. So this is a 30-minute horizon, and about 1-2 years ago, a model, if you gave it a task that would take a human to accomplish in 30 minutes, a model could do. Now we're at a point where models can accomplish a task that would take multiple hours for a human to do and have a 50% chance of getting it right. So that's fine. I mean, when we're talking about long horizon, we're talking about a task that would take you or I days or weeks or months. The longer and longer, that's long horizon. And the reason why it's difficult to do long horizon is because if you think of a task, say it has 100 steps, say in any given step, there's a 99% success rate for the model in that step. So you have 100 steps, 99 to 100, you will eventually, I don't know, I'm not doing the math, but it's probably 20, 30% at the end of that. So at the end of those 100 steps, there's probably a 20% chance that it succeeded, which is a pretty low rate of success. So we need to get the models to where they can succeed, close to multiple nines of success rate in any given step. And the models need to be also smart enough to detect if they've chosen a step, gone kind of off course, and then recorrect and try again. So there's there's work to do as part of long horizon um, where we want to get to. Let's dive more into what's going on in post-training reasoning. Here is a thinking trace. So, solve a math equation, and this is the model thinking over here in this right-hand side box, and then it gives a final answer, aiming for the answer to be both high quality as well as helpful, safe, and respectful. So originally, post-training was using supervised training, fine-tuning a model. So this is an example of, say, an SFT data set, which is given a particular prompt. Here's the answer. Here's another prompt. Here's the answer. So you could you could basically force the model to know what's the right answer given a prompt by giving it examples of prompts and right and wrong answers. But that's not really thinking. That's just imitation. So RL is where now you you actually train the model to try a number of different reasoning generations, a number of different steps, and you reward the model when it chooses a particular generation that is more correct than the others. So in this simple example, uh, rollout is essentially opportunities for the model to respond to the question. And uh, the first one is looking more correct, so we gave it a reward of 100%. Good job. The response 2 is not very helpful at all, so we gave it 0 reward. And this one created a ticket, which is just a really bad. I did not ask this thing to create a ticket. I was just asking to give information. So the reward is just, we completely mark, we don't want this response at all. So that's learning through exploration. I'll pass this one. So how do you actually determine the reward? So we have to create a reward model. And this is a simple example of training a reward model where given a prompt and a response candidate, the reward model, it outputs a particular reward. In this case, we're showing an example where a reward is not just one number, but a vector saying how helpful, correct, coherent, complex, verbose this particular prompt was. There are two main categories of reward models today. The first category, verifiable rewards. These are fairly intuitive. These are rule-based rewards where they can be verified, completely whether it's true or false. So for example, math, you can verify whether the response is correct. For code, you can execute the code, run unit tests to verify if the code is correct. Instruction following, you can verify if it followed the instructions. So these are high, very easy to verify and very easy to assign the reward based on how verifiable it is. There's also a class of model-based rewards where it's less verifiable. It's maybe more objective, and so this is where you can have say models reasoning as a judge. LLMs, you can use an LLM to actually judge how correct a particular response was. Okay, so this is going through. So today, there's many different algorithms used in RL. One of the most common ones today is this algorithm called GRPO. It's essentially a group-based policy algorithm. So here, policy is the model that we are trying to train and giving it, we want to give this model thinking ability. So we give it a prompt. And so one of the examples earlier, or here it is, solve this math problem. And given that prompt, we give the model, uh, say, 16 tries, generation n, 1 through 16. Now, out of these 16 tries, then we pass it through a separate reward model, which we just discussed, to score the reward for each of those 16 tries. And here, you know, only one out of the 16 was correct. And then we take the average of the group and we update the model with with that average and nudge the model towards the more correct generation. Um, this reference model is essentially just making sure that the original model doesn't stray too far from a particular RL loop. And so this is an iterative process. The key takeaway here is that you can run this GRPO loop many, many, many times with actually not, you don't need that many prompts. You don't need that much data. As long as you have a decent reward model or multiple reward models, um, the model will get smarter. It'll keep getting smarter. There will be a point of saturation where there's diminishing gains. Uh, but this is, if you remember that previous slide at the very beginning, the post-training scaling law and test time loop scaling law, this is where that comes into play, where the scaling law becomes more about the number of iterations that one does to make the model more intelligent, not how much bigger the model gets, but just how much more we refine the model. And so this is essentially benchmarks. We can see quantitatively after you can see that the model got much smarter, for example, in this math rewards upper left, after just 100 different loops of that algorithm of the GRPO. It still kept getting smarter until about 800, 600, 800, then it leveled out. Here in one other thing you can see here, generation length. This is how 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 much more is the model thinking, like in its generations, like how much more thinking tokens is it using. So you can see after more and more loops, it also grows in its thinking output, which is something actually one needs to balance. You don't want the model to be thinking so long, then it becomes kind of like, okay, it's thinking too long. I don't want it to think that long. I want it to be smart, but not think too long because I still need to get my job done. You know. Okay, and this is an example of what I was discussing. That at a certain point, token budget, that then the intelligence here, the accuracy um, of how it's how accurate is it in beating those benchmarks. It does plateau, so you don't need to. Essentially, I don't want the model. I can limit the number of tokens that the model spends thinking, and I'll have reached the highest level of intelligence that it can get, and that's okay. So here's some tools that NVIDIA offers, NeMo RL and NeMo Gym, to accomplish what we were just discussing. This is basically a high-level picture of GRPO that we were just discussing. NeMo RL being the library that we can use for generating. We'll go into more of that. And then NeMo Gym is offers these different verifiers and environments as part of that RL process. Verifiers, we kind of talked about this before. This was where you can have, rule-based, LM as a judge, Um, these are essentially uh, different ways of providing a reward score for a given model's prompt generation. Okay, so RL ingredients. Getting back to what you can uh, expect from NVIDIA to provide. NVIDIA is providing Nemotron models. You can also, of course, pre-train your own model or take any other model from open source and start with that. We are also providing different data sets. We discussed open environments. So NemoGym, we have a number of different environments that we provide for, say, math reasoning, science reasoning, coding, instruction following, engineering, search, chat, agentic tool use, and long context. So this is an example of how much reasoning improved the model's intelligence. So ne Nemotron V2 was released earlier in 2025, and it was getting a score of 15 in the Artificial Analysis Intelligence Index for small models. You can see that um, Nemotron version 3 and the difference between V2 and V3, not that much architectural difference, but more so we added this GRPO post-training loop to it. It improved its intelligence by 67%. Okay, so this is an example where in one of those GRPO loops, multiple environments are meaning essentially multiple reward models. So in one given loop, we would have the model try to provide multiple generations for a prompt um, and see how it's scored against multiple different environments. All right, we're going to get into NeMo Framework a bit here. So this is a bit of an overwhelming slide, but if you go to this GitHub URL address, you'll be able to see all of these different NVIDIA NeMo repositories, and these are all available open source. And what we are providing is end-to-end, what one might need to train their own model and pre-train, post-train, and then even deploy for inference. So we have these data generation and pre-processing libraries, um, pre-training libraries, Megatron Bridge Auto Model, post-training RL and GIM, and then various inference-related libraries. All of these are developed out in the open, and also if you find them useful, you're also welcome to submit your own pull requests and help us improve these repositories. We welcome open source contributions anytime. All right. Just some shout out to Megatron Bridge. This is a project that provides optimized recipes. When I say optimized, meaning these are recipes for training models that are optimized for NVIDIA specific hardware. An example of this is we have recipes in Megatron Bridge for many, many models. Um, you can pre-train DeepSeek V3 or Qwen 3 if you want in Megatron Bridge, and so this is different hardwares from H100 to Grace Blackwell, the most recent Grace Blackwell being GB300. So you can see for what we're showing here is this is different data types, BF16, MXFP8. If you're wondering where NVFP4 is, those numbers we're optimizing those recipes as we speak. So I didn't have them available for this slide, but we'll have them soon. But essentially, you can imagine NVFP4 will be even higher number of teraflops. If you're not sure what teraflops per GPU, just think of it as the getting the most efficiency out of the GPU. So uh, you can see FP8 versus BF16. Essentially, MXFP8 is using half the number of bits, and it is, as you can expect, more efficient than BF16. And NVFP4 will be even more efficient, but there's always a trade-off between low precision and accuracy. And then what this different graph is showing is within a given data type, for H100, you're getting essentially, you know, three over here, like 3x boost, BF16 going from H100 to Grace Blackwell. In FP8, you're actually getting 4 times boost going from H100 to GB. NVFP4, I think that's going to look even higher, more like 5x plus boost, which is meaningful in the sense that, okay, if you're training the model and it takes 5 days and you just switch to a better hardware, you can bring it down to 1 day just by using a higher class GPU. Okay, let's talk a little bit about how NeMo RL, this GitHub project, fits into the the training that we were just discussing. So this is kind of like a high-level set of features that NeMo RL, the project, provides. We talked mainly about GRPO, the algorithm. There's many different RL algorithms, and so there are many of these are supported in NeMo RL, and there's new algorithms coming out all the time. I mean, one is actually this is missing PPO, but like BPO, PPO, DPO. So SFT was probably the main algorithm like 2 years ago. PPO, DPO is the main thing 1 year ago, and so now we're into the GRPO, GSPO, DAPO regime, and so you can expect the algorithms in the RL space are evolving very quickly. What is considered state of the art yesterday becomes quickly outdated, thereafter. So one of the challenges is we want to also make sure that the most latest meaningful algorithms are supported in RL and available for use. Training backends. What does this mean? So you can basically choose a path where in auto model we have a backend where it is essentially compatible with pure native PyTorch and using native PyTorch parallelisms. And the advantage here is you get access to a large number of models. There's essentially any model on Hugging Face you can use on NeMo RL. You can post-train it on RL using the auto model backend. Megatron is a more optimized backend. The numbers that I showed you earlier were using the Megatron backend. The only thing here is the Megatron backend just has a subset, smaller coverage of models. And generation backends. So this is where we are in that GRPO algorithm. We were prompting the model that we are post-training for outputs for generations. And here we support different inference backends. So VLM, Megatron inference. SGLang is actually another one that's upcoming. And we, in the end, we use Ray for orchestrating. On the performance side, there are a number of different model architectures supported. We have large MOE with all kinds of parallelisms. We support FP8 end-to-end with accuracy matching. And as that previous slide showed, you do get a 20% speed up of using FP8 over BF16. So just showing that you can use FP8 end-to-end from pre-training through post-training with RL. And NVFP4 is coming soon. Async RL, I won't spend too much time talking about that, but this is essentially a feature in NeMo RL where you can do something called off policy post-training. you can basically scale out with more infrastructure using async RL, and so you do get, um, yeah, I would say more optimal end-to-end performance in the RL loop. Okay. Uh, all right. So this is motivating why one could use a NeMo Gym project. So when one is training, doing post training, um, there needs to be something that's orchestrating the different tools that we were discussing, the tool calling that a model can use, um, different all the different environments. Those can become different servers and resources that need to be managed as part of the RL loop, and um, yeah, being able to have uh, an orchestrator that manages the data and the rollout efficiently across the policy model and the different environments. So our answer to that is NeMo Gym. NeMo Gym is this orchestration layer for that you can use with NeMo RL. NeMo Gym is compatible with other RL frameworks, but it's highly optimized for NeMo RL. And it's been battle tested, meaning that NeMo RL, NeMo Gym were used to post train Nemotron 3. And we are using it currently for the super and the ultra variants. So where does NeMo Gym come into play? So here's an example of preparing a training environment. You start with your benchmark model and what are the capabilities that we want to add to this benchmark model. And we can use existing environments that NeMo Gym provides. You can also develop your own new environments and add those into NeMo Gym. And that prepares the gym environment. Now the gym environment is ready and we can begin the model training. You start training your model and verify the trained model against benchmarks and validate capability improvement. Oh, I am reaching the end of time here. Okay. Um, this is a more pictorial or graphical view of what's happening between NeMo. So RL is the training framework on the left-hand side, and Gym is the gym environment on the right-hand side. So what we have going on here is the policy model itself is hosted and trained inside the RL framework. When we do a given GRPO loop, we'll send the the prompts to the agent coordinator in NeMo Gym that will call the model or models to do the generations, that 1 through 16 attempts. It'll pass those generations to the verifiers or the environments and get reward scores for each of those generations. And it'll take the output from those and bring it back into the training loop for RL and update the weights for the original model. And so this given loop is GRPO brought down from conceptual level into how it's actually the pieces that are involved in the RL and NVIDIA NeMo RL and Gym projects. Again, you can extend NeMo Gym. You can bring your own verifiers. You can bring your own training data and different HTTP endpoints to act as resource servers. These are the ones that are provided out of the box by NeMo Gym. We talked about them a little bit already. Okay, so I'll just end with a couple of slides about how Nemotron 3, how we went from the pre-train to post-train. and deliver the final model that is now available on Hugging Face, given the context of everything we just discussed this past hour or so. So we started with pre-trained data. There's 15 categories of pre-trained data. We'll get into these in different slides. So we did the pre-train, extended the context. This is where we made it extendable to a 1 million token context. So now you have your pre-trained base model. That pre-trained base model, then we ran SFT on that pre-trained base model. We gave it reasoning control, and I'll talk about that in the next slide. And now you have your fine-tuned checkpoint. That fine-tuned checkpoint, then we ran it through an RL. This is a GRPO loop using RL with verifiable reward models. So RLVR via GRPO. Now you have your RLVR checkpoint. Then we ran it through RLHF using reward model, the help steer data set. This is what I mentioned it earlier, where it has those different 5 categories of safety, helpfulness, accuracy, and so this is another loop. And then we ran it through RLVR again via GRPO. We have the final BF16 checkpoint. We ran post training quantization to shrink the models down from BF16 to FP8 data types. So it's actually half the size now, and half the size, but still just as smart. And so now you have your final FP8 checkpoint. Going into pre-training a little bit, Data Designer is a project that you can use for synthetically generating data. When you are to help add more data, you can use Data Designer. Okay, base model. This is the architecture. It's a hybrid Mamba 2 MOE architecture. So the unique thing here is back originally, all the LMs were attention, very expensive. So now we're using Mamba 2 with MOEs, and there's only very few attention blocks in the overall architecture, which is how we've been able to have both long context and efficiency. This is the SFT loop. The main thing here is you're able to turn off on and off thinking we train it with some small percent of the samples had this thinking end of thinking token. So the model became aware of what it means to turn on and off thinking. And finally, the RLVR loops. And here's a slide just talking about NeMo RL. Again, just that one URL I showed earlier, you can get to all of these things. So yeah, you can take a picture or just go back to where is it? This one. Just go here. It's all there. Thank you very much for your time today. Hope this was somewhat helpful. Appreciate it. Thank you. Oh.